All right, given the figure here, the geometric figure, we are asked to find the distance from N to line LM. We need to pick the shortest distance possible. So we're going to go from N to O, which is a distance of 6.8. All right, so given our geometric figure here, we're asked to find the distance from point Y to the line WX. So we want to travel this distance right here. Going along that path, that's a terrible line, I'm sorry. Oh well, you guys know my art skills. Okay, so we're asked to find that distance. The problem is it's not given to us, right? So we have to think, gee, what could we use? Well, in my very first video, we talked about Pythagorean theorem, which is a way to find the length of a third side of a right triangle. Lucky us, this happens to be a right triangle. We have a length of the leg and the length of the hypotenuse. So using Pythagorean theorem, we can now find the length of this third side. So we will take our leg, that's 10 squared, plus our second leg, let's call that B, equals our hypotenuse. I'm going to put that in parentheses to make sure we understand that the whole part of it is being squared. So 10 squared is 100. Again, 10 squared is 100. And the square root of 2 squared, that cancels out the square root. And we get 2. Whoops, sorry, I was getting ahead of myself. We get 2, and 2 times 100 is 200. So now we are going to solve for B. B squared equals 100. So this side length is the square root of 100. So B is 10. So in other words, the distance from Y to the line WX is 10. Okay, here's our new geometric figure. We are asked to find the measurement of angle RCP. So we want this full angle measurement right here. Part of the angle measurement is 35 degrees. That's from D to C to P. We do not know this one. So we cannot figure out the full angle measurement. So we're going to use our deductive reasoning to see what we can do to figure this out. We know that both of these sides create right triangles. We're given the little right angles. We are given that R to D measures 11 and P to D also measures 11. So those are congruent sides. Now the beautiful thing about these two triangles is that they have a common side. This one right here. They share that. So that would mean that their shared side is congruent. It's kind of like a reflection of itself. So therefore it is congruent. And so we have our hypotenuse of both triangles, and we have a leg that is congruent in both triangles. So by the hypotenuse leg theorem, these two right triangles are congruent. Now what does that mean about our other angles? For example, angle RCD compared with angle PCD. Well, that means they have to be congruent. So this angle is no longer a mystery, but is 35 degrees. So if we want to know the full angle measurement, here, let's grab a new color, make this more exciting. If we want to know this full angle measurement right there, then it would be 35 plus 35. Which is 70 degrees. All right, so here's our next geometric figure. We've been given triangle ABC. We can see that it's been split so that A and B have been cut in half. D is the midpoint of A and B. Here's a point. So these two sides are congruent. and these two sides are congruent. That has all been given to us. What we are asked to determine is, given this information, is it true that line CD is perpendicular to AB? So that is written as we're asked to find, is it true that CD is perpendicular to AB? Is that true? Well, let's do some work. Let's think about this. So we have two sides given to us. The third side, you can see these have been split into triangles by line CD. Just like the last problem or example we went through, if they have a common side, that common side is always congruent to itself. So we can say that that side is congruent to itself. So by side, 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 we have triangle ADC is congruent to triangle BDC. I'm running out of room. Tiny whiteboard. Okay, so these two triangles are congruent because all three sides are congruent. What does that mean for our angles? Just like the last problem, that means all of our angles are congruent. So this angle is congruent to that angle. These two angles are congruent, and that would mean that these two are also congruent angles. And since, well, let's backtrack. Since these two are congruent, this line is an angle bisector. It also splits that in half, so it is a perpendicular bisector. So therefore, CD is perpendicular to AB. All right, here we go again. We have a new figure, geometric figure, and we are asked, is angle ABD? So angle ABD, that's this one. We're going to follow A to B up to D, so it creates this angle. Is that congruent to angle CBD? I don't know. So let's see what we can come up with. Can we get these two triangles? Can we get triangle DCB to be congruent to triangle DAB? Let's see if we can. If so, then we know these two angles are congruent. Okay, so we have been given, well, first of all, they're both right triangles. So we need one of those four theorems that we talked about earlier. We have legs are congruent. That's been given to us. And we have a common side. This one right here. This is our hypotenuse. So we know this is congruent. So then we have, because of hypotenuse leg theorem, we know that triangle DAB is congruent to triangle DCB. So because these two triangles are congruent, we therefore can say yes, angle ABD is congruent to angle CBD. So yes, it is. All right, here we go with another example. So given this geometric figure, or our triangle ABC, we are asked to find if AB is perpendicular to CD. In other words, do these form a right angle? Well, I don't know. Let's figure it out. So we are given two sides are congruent. We have a common side, so it is congruent to itself. And looking at the figure, this is all we can do. We have one side given to us. We found one side. That gives us a side. We know nothing else about this figure, so we cannot with any certainty say that they are perpendicular to each other, that CD is perpendicular to AB. So we don't know. All right, I'd like to go over a definition. I'd like to talk about perpendicular bisectors. So a perpendicular bisector is a line that meets another line at a right angle, and it also splits it perfectly in half. So this is actually a line segment. We have A and B here, and it is being bisected by the line segment CD. So CD and AB are perpendicular. This little symbol means perpendicular. So these two line segments, sorry, I should have done that. They are perpendicular to each other. Again, they meet at a right angle, and CD splits AB perfectly in half so that from A to D is the same distance from D to B. So this is an interesting little phenomenon because a lot of times a question will pop up saying, if you have a point that is on the perpendicular bisector, so I don't know if you can see that point, I'll try to make it larger. Okay. Is this point equal distance from B and from A? So you're going to get this funky triangle if we draw lines down. Are these two sides, these two imaginary sides of our triangle, are they congruent? Or in other words, is this point the same distance from B as it is from A? And the answer is yes. So this point creates congruent sides of a triangle. Also good to note is that if you were given a point, okay, let's say you are given a point that is equal distance from two endpoints of a line segment, that would mean that it would have to be on, so this point, if you're given this random point, we should call it something other than C. We'll call it F. Okay. Point F is equal distance from B and from A. That means that point F is on the perpendicular bisector of A. So it goes both ways. If it is equal distance from A and B, it's on the perpendicular bisector. If point F is on the perpendicular bisector, then it is equal distance from both A and B. Okay, the last thing I'd like to go over is the angle bisector. So this is a definition. If you're given the angle ABC and you have a ray cut through the angle so that it bisects the angle, meaning these two parts are equal halves of the original angle, then any point on our angle bisector is going to be equal distance to the two sides of our angle. So these two will end up being equal. Also, we can say the converse of that, or not the converse, but the reverse of that, that if we are given a point that is equal distance from two sides of an angle, so we're given this point, we'll call it point F. I always forget to name it, don't I? Okay, if we're given a point F and it's equal distance from side, or yeah, we'll just call it side A of an angle and side C of an angle, then we know that point F has to be on the angle bisector. Just like our perpendicular bisector definition and a point line on the perpendicular bisector. So that is useful tidbits to know.